What I want to present here is some kind of work in progress, but based on this summary of many works that was done the last years, which was mainly focused on spectral deferred correction. So if we, well, the SDC as itself was introduced in 2000 by Dutt and Granger, and well, it was based at first on the idea of deferred correction. What actually bring SDC was the idea that instead of doing the correction using, of writing this derivative deferred correction, we use the integral, or some integral deferred correction. And also they added the spectral aspect, so try to have some Gaussian nodes to the integral is even more accurate than the normal integral on regular nodes. So that was really what brings actually a lot of idea later into parallel time. And that was, for instance, the first time I remember for parallel time method using SDC was this pipeline approach. So if you, the base SDC idea is that you decompose into different intervals and then you sweeps, you correct each interval solution, which has several nodes. So you can see at several, the nodes as stage of Runkeler method, for instance, and then you correct until to a point where you say, okay, my solution is fine enough, I transmit that for the next time step and then correct it again. The first idea for parallelization was to say, hey, I can actually already transmit the solution to the next time interval without having already computed the final solution. That was the idea of Guibert and Tromer-Dervoux. They applied that to some CFD problem. It's a really small paper, like conference paper, and I didn't see any reference. I don't know any reference before that. So they basically introduced this pipeline SDC, where you saw first the first sweep on the first interval, then you have a solution to transmit to the second interval, and in the same time you will actually compute here the second sweep for the first interval. Then you do the same. Here you transmit to the next one, you can compute the second one, you can compute the third one, and you see here all those three stages can be done in parallel, and you can continue in some kind of pipeline fashion. So this was also done the same idea with Riddick. So Riddick kind of say, I don't want to decompose into several intervals, I just want to use regular nodes, so at the end I can use some shifting stencil. So I use, for instance, those 4 nodes here, and then I compute this one here using all those stencil nodes, which allows me to also in the same time compute the previous one and the previous one here, but always shifted, which allows me to use, what Alex presented with this Riddick thing. And at the end, it was also FAST, so FAST came after that. It was a bit inspired from parallel, with the main idea parallel, in the parallel iteration, you have this bound 1 over k for the efficiency, the number of iteration basically, because every time you iterate, you call the fine solver, it costs a lot. So FAST, base idea was to say, I don't want to use the fine solver, I want to use something that is approximate, and then I use the same idea of multi-level with a coarse and a fine grid and try to have something that is more efficient. So I will come a bit more later into FAST, but that's the kind of illustration that you can see. For instance, you have also these different intervals, which are basically the interval of an SDC sweeps. But you first start with a coarse sweep on a coarse level that is cheap. You do only 1 for the first interval, 2 for the second interval. So it's mostly the initialization that is a bit specific, but then it allows you to have this pipeline also parallelism using the fine sweep that cost a lot, but are in parallel, and then all the coarse sweep are done in sequential. So a bit like in parallel, what you have. That's the same idea, almost. And in my case, so I worked on SDC, and I wanted really to optimize the SDC in the sense that you have a lot of parameters. You can change the coefficient, you can change the node, you can change many things. But how can we eventually tune or design the SDC method such that it's converge faster, or it has some good properties or something like this? So the basic idea is to start on Dahlquist program, and I will actually stay on the Dahlquist problem for my whole presentation. Doesn't mean you can use that for other stuff, but at least it's kind of, for analysis, as to start to design new method, it's a good start. Huh? And don't worry, the lambda won't be a real negative number. That would be a plain imaginary number. So at least I won't have a diffusive problem. And so I start from my SDC interval. I do have my starting point, my initial time of the interval, the last initial time, and the nodes in between with some spacing that can vary. And I write the discrete collocation problem. So that's what some people already presented with this Q matrix. So after writing this thing into integral form, so u is equal to u0 plus the integral of lambda u, then you can write that for all the nodes, and for all the node solutions that are here, you have specific coefficients that are linked to this integral that you would compute here in the Q matrix. So the collocation is basically a Runcuda method. You can actually replace all of this with a Butcher table, and that would be the same problem that you're solving with a Runcuda method. So if, for instance, you have a strictly lower triangular Butcher table, that's some explicit method. You don't need actually to inverse this system. You have one way to basically compute it only with explicit evaluation of lambda u, which is less expensive, and that's what explicit method. No, the what SDC does is I look at this problem. I only consider dense Q matrix and I want to solve it using a lower triangular method precondition. So this P here, and this P is actually the precondition iteration applied on this problem, where I select this particular approximation for Q delta. So until now, nothing very new. And this whole analysis was actually done, the first time I saw that, it was in this paper from Hang and Jan Minion, because originally SDC was presented in node-to-node fashion. So it's not really written like this in the original papers. This is another way, which I call node-to-node in contrast to zero-to-nodes in contrast to node-to-node. But at least from the analysis and to design, it's to design new algorithm is quite practical. So that's where we are. And what we wanted to do with parallel SDC, I mean, I don't want to say parallel SDC because there is many versions of parallel SDC, so I will call this diagonal SDC, at least to distinguish with this block-gauss-seidel or pipeline SDC. It's basically to say I can use a Q delta matrix that will be diagonal. In that case, I can do the sweep, and each node update will be independent from the others. So I can do that in parallel. So it's small-scale parallelism. And what I do have here is a problem where I do have to select which diagonal coefficient I want. I don't need to diagonalize the Q matrix, which is one of the versions. I mean, something that was done with paradigm or what just presented. Here, I just say, I keep the matrix as it is. I just find a diagonal preconditioner. That's the only thing I do. So nothing really new. What is new is how to select the coefficient. And I focused on this SDC iteration matrix. If you write it down with all the analysis, the preconditional, and so on, that's what you get here. So that's the iteration matrix of SDC. You see, it depends on lambda delta t, and we are considering Dahlquist, but at least we see exactly what happens that depends on the problems and the time step. And that's what comes from the method itself. In particular, this term here, which doesn't depend on lambda delta t. I mean, we don't see that explicitly here. It's actually here. But yeah. So we want to optimize coefficients, but the idea behind this was say, I don't want optimization to be problem dependent. So I want to remove this lambda delta t dependency. How can I do that? Two ways. I push it to infinity. So that was the idea of Robert Speck here. And then I get this stiff limit, which is basically this term. If you just write that down, the limit of this when you have lambda delta t that goes to infinity, that's basically that. Or what I also looked at, I mean, some other people here in this paper already look at something similar than this. It's actually looking at non-stiff limits. So I divide by delta t, so I remove this, that actually makes something tends to 0, and I look at this whole terms here. And when I have lambda delta t that goes to 0, that will be my limit. And so the whole idea of the paper that we wrote later, so this paper that were mentioned from Gaia and myself, and Daniel, Sebastian, and Robert Speck, was actually to, instead of looking at, I mean, previous idea was to minimize the spectral radius of those things. So we have some coefficient here that we don't know, and we try to minimize the spectral radius. This is a really hard problem. Why? Because the Q matrix is kind of really badly preconditioned. And when you get all of this, it's really hard. This is actually a bit easier than this, but still, it's the same problem. So you don't want to compute that numerically. Yes?
The second limit, then you add the lambda delta t again? Because you divide it by lambda delta t, otherwise...
You will add it in the integration matrix.
Add it again later.
What you look at is actually without the influence of the delta t at the end.
Just add it again.
Yeah. I mean, in the method, yes, you don't only use that in the method, adjust the matrix you target for the optimization. So forget the spectral radius. It's really hard, although it can give some result if you use some really fancy optimization algorithm. But so instead of that, we look at nilpotency. That's the main idea of the paper. And I won't describe all the development we did in there because that would be a bit long. I would need maybe more than 20 minutes. But the whole idea is say, instead of searching coefficient that have make these matrices having a low spectral radius, I look at coefficient that make the matrix nilpotent. And starting from that, we can continue that. The whole analysis also was done using polynomials. That means we don't want to do this optimization, this analysis in matrix space. We just say that this matrix space is actually equivalent to isomorphism to polynomial space. And in this polynomial space, the operations that are done by the Q matrix, that's an integral. So that's the integral of polynomial. I know that. I mean, I can actually easily compute the integral of any polynomials using the monomials. And this is actually how the proof is done. And that's actually gave us some nice result at the end. The first one was this min SRNS. That's what the original ones that we get, the first, because it was the easier to get. And we noticed that at some point, if you take the nodes divided by the number of nodes and you use that as coefficients, then it makes this whole matrix nilpotent. I mean, it made this matrix here nilpotent, that's all. So we find directly by taking the node, dividing by m. The whole process of finding it was a bit tedious. I won't tell the whole story, but at the end, we realized that and then prove that we have to use this whole polynomial analysis, and it was kind of nice and easy to see at the end. The second one is something we didn't manage to get analytically because it was really hard. It's still really hard, and maybe one day we'll find it, but for now we don't have. So we kind of did a trick, because if we consider this is nilpotent, that means the determinant of this thing is 1. So instead of solving the spectral radius, we minimize the coefficient here, considering this. I mean, by replacing z here by all the nodes, we have m equations. So we just solve this. It's a nonlinear equation, and there is plenty algorithm that allows you to do that. We also impose some condition that the diagonal coefficient we obtain are always increasing. I mean, increasing order, which is just a rule of thumb. I mean, something that I notice help for the stability. But at the end, yeah, so everything is kind of implemented in this QMAT library, and it's automatically computed now.
Is it obvious why this makes it nilpotent? Can you just say?
I have to remember that, but the nilpotency is based on the characteristic polynomial of the matrix, and this is basically one expression of the polynomial character. I mean, I don't exactly remember why.
I cannot see it, but I believe you, but it would be nice to know.
I think it's probably written in the article, so I have to look at it again. And to be honest, that's mostly Gaia who actually found that, so I was just understanding it afterward. I focus more on this implementation and the idea of using the nodes, for instance, but yeah. I mean,
it's related to the characteristic polynomials.
Yes.
All
you have to write down the characteristic polynomial of the matrix. Then there is one theorem in algebra that say that if this is the characteristic polynomial and you have some properties, then this determinant of it's the identity minus something. So you see it's identity minus z times the matrix. So I minus z the matrix. So the matrix you have is I minus this. So here you have minus plus. And that's basically looking at this here. I just compressed the formula.
Tau.
That's the nodes.
Was the node location, right?
Yeah, this property here can be written for any value of z. And I noticed that using the nodes was actually kind of an optimal choice. But so there is. And then the last one, we still wanted to find something that minimized so this thing, I mean, that make this thing nilpotent. And we realized that we cannot do that with constant coefficient, but we can do that with coefficient that varies. That means for the first iteration, you take the nodes directly. Then for the second iteration, you take the node divided by 2, and so on, and the last one. And actually, when you compute all this with this polynomial analysis, you will retrieve that this is actually nilpotent. Good, we have something. We have to change the coefficient. It makes the implementation is this a bit harder because you have to change your linear solve for each iterations, of course. But at least we have something that is analytical that we can use. So we have 3 candidates, and it doesn't matter which node we use. It doesn't matter, we can change the node, have uniform, non-equidistant, whatever. At the end, it's just a basic result if your Q matrix is a collocation on the node. So once we have that, there was many results that was already shown by Thomas, by Abdel and others. And I just want to underline that we test that on the paper on using PySDC and using some parallel implementations. And we compared it with standard method that was also implemented in SDC, for instance, on this 1D Alan-Kahn nonlinear PDE. And we really noticed with some error versus cost that it actually helps. And what was really nice is like the standard SDC approach, the LU preconditioner, was already good. I mean, that's something we know. I mean, it was some comparable performance as this ES-DIRC, I mean, this diagonal implicit Runke method for stiff problem. But because we can use that in diagonal, I mean, we have this diagonal preconditioner, we can use the parallel, so the cost actually reduced because of the parallel computation. So, and this was some coefficient that were actually already founded in the paper of 1991. So where they actually did also this for the first time, and they used some numerical approach to find the coefficients. And well, those are good already, but we could actually improve that. And we see, I mean, what also we noticed is that for ODE, usually the min SRS was better, while for PDE, the min SR-flex was better. It's still not sure why, but we noticed that for PDEs, this min SR-flex, so changing the coefficient, improved the accuracy, improved the stability, and have some really nice property. There is also other application. We can combine that with IMAX, even if it's not designed to, it actually works. So that was kind of a luck. It works for this IMAX problem. So we just use this minus R flex for this implicit term and this peak characterization for the explicit term. Was great, but still there is a lot of analysis and a lot of design, I mean, optimization, design optimization missing here. But yeah, that's, if that was not like this, it would be a bit boring. So still a lot to discover on this. And one thing I can consider is, well, I do have one way of doing some diagonal sweep. I can parallelize that, and I see it works in many situations just for SDC. What would be if I try to combine that with fast? So if you want to understand fast, well, you need a bit of time. I don't want to make you understand fast. I can recommend the paper. I mean, this paper here was originally built to develop convergence bound. And those convergence bound were really good for scalar problems, but as soon as you switch to matrix represented problems, then it gets really bad. So the convergence bound at the end was a bit disappointing, but what was really nice is that we had to write every method, so fast, high multigrid, parallel, into one same framework to actually apply everything. And this allows to kind of understand fast in a really simple version. We only consider time dimension, and it's just a two-level algorithm. I mean, you can see that as a two-level algorithm. Fast is not only two-level, but if you see it as a two-level, then you see actually what it does. And for now, I will consider that I do have, like, for instance, a given number of time steps here. I write this collocation problem on each time step. I have the transmission condition that actually give the final solution of the previous time step to as initial solution to the next time step, so this H matrix, and I write my all-at-one system. So what basically Judge did, it's the same idea. Now, fast use this on the fine level here that you can see here that with 4 intervals, and I can say I define a coarse level that only have 1 node per interval. So that's a coarsening here by a factor of 4. And then I will alternate between sweep, so SDC sweep, where I apply this SDC ID on each block. But on the fine level here, so this one, I will do each sweep in parallel. That's what fast does. So all together, while on the coarse level, it has to be sequential. So I do the sweep for this, then the sweep for this one, then the sweep for this one, and so on. So same a bit as parallel, except parallel will use here not a sweep, but the exact problem. So parallel will solve exactly this on this thing, so that will be more expensive. So the interest of fast is it's less expensive to do a fine sweep. Now, I want to, so as I say, I don't want to make you understand that. I want you to show what happens. So that quiz problem, I consider lambda is equal to j, and this delta t is equal to p over 4 for each small time interval. So what I would have at the end, the collocation solution of my problem will be this circle. So if you solve this dark with the disk coefficient, you will actually have a circle in the complex plane. And I mean, if the solution is exact, then it stays on the circle. And then you can look from this. I mean, if you go that way, that means you have a diffusion error. And if you are not here, but here, you have some either phase error. So positive phase error, negative phase error, and so on. So it's a nice way to see how your method behave. And as I say, fast, just I use so radial nodes on the find block and just one node at the end of the interval. So I start with the coarse sweep on the coarse level. That means I compute here the first solution here. So it's like a backward order, but then I interpolate using some linear interpolation to have the solution here. And then I do this thing and this thing. And that's what we see here. That's the coarse sweep of fast that is done in parallel. Now, then I use, for this one, I use the fine sweep, so the relaxation, you can see it like this, which will always start from what it has already and then improve that. And you see, because it is in parallel, you see this discontinuity because of this uncorrelation between all the solutions. But then if I continue for the second iteration, then I start again the coarse sweep. So the coarse sweep will start from this solution, this solution, this solution, and this one. It improves again. So I get actually a better solution, and I see it's actually converged. So that's only the second iteration, but at least you see that. Now, the idea, say, okay, here when I do this coarse sweeps on the coarse level, I have to do this sequentially, but I can also write on this coarse problem, it's a collocation problem, right? Just uniform nodes, but I can write the whole collocation problem this. So that's what I would write, basically. It's just applying the idea of one interval, but on all the intervals together, but only a coarse point, so I have less points. And then I want to replace this sequential coarse sweep first by a direct solve with this coarse operators. So I want to solve exactly for now. I mean, at the end, I want to do something parallel, but for now, I just want to check if my method works by doing a course correction that uses all these points together. It's not separated as it was before. So the restriction is already there, and that's I go from this grid to this grid. That's what I had in fast. And the interpolation here, I can either say I use some linear interpolation between the point, or because I have all the points, I can use some barycentric interpolation to the fine grid. So at the end, doesn't change much, but and I do the balance. So I do that first, and then I go to parallel stuff. So if I look to the Dalquist problems, so same settings here, and I do one LU sweep and so on. This will be my first iteration of the problem. What I see here is it doesn't work at all. I mean, I use the core solver exactly, and that's fine. And it gives me something, I mean, I don't represent it, but if you actually look at what's in it, it's like something like this, something really, really bad. And then the fine sweep, I mean, the fine sweep tried to correct it, but it's already, I mean, the course solver is already so bad that the second iteration, yeah, give me something really odd, so I don't like it. There is something weird here.
Can you explain again what you do differently? I don't understand what it means applying the course solver globally.
So instead of solving step by step,
which solves the course problem,
I use a collocation, so a dense matrix on the course points.
Different method, basically.
Yes. Yeah. So I solve, and actually I will maybe show you a bit later what it is. So there is a problem when I do that. And the problem comes from the formulations. Node to node, zero to node, actually. If you look at what we had from a zero to node perspective, so in fact, what is done on the original method in fast, it uses some backward order step in between. So if we represent this AC matrix, that will be this one. You do one backward order step, then use the solution for the next one, and so on. It's here the zero to node formulation, and that whole fast is built because, well, we have some sequential way of seeing this whole at once matrix. So the course matrix will be also following the same way. But you can also imagine that rather than having this sequential approach, you have these node to node formulations. And if you look at this, you basically sum this thing here, then sum this thing here, and so on to the end. So you have this matrix. And here it's the node to node formulation. So the right-hand side is actually all the initial solution for all the vectors. And that's kind of closest to what we have with a budget table, this zero to node formulation. Rather than solving node, we solve zero to node. At the end, the only thing that changes is the matrix that you have in between. If you multiply this by this, you get exactly this. And it works also for nonlinear. I mean, it doesn't matter here that I'm just looking that way. It's just the same for any operators. That kind of addition between different lines. You just reorganize the problems differently. So, okay, let's try to apply that. So if I have my all at once problems, this all at once problem is actually, as you see here, it's a node to node formulations because we first start from the first node, first block in some sense, and the second one and the second one. So the solution that we will get by restricting to the course grid is in node to node form. So we want to, instead of having this classical restriction from fine to coarse, we multiply this by this previous matrix, and that's what we get. So that's what we had originally. We just take the final interval solution and we transmit to interval. So now what we will do is basically the first interval will propagate, we use the initial solution that stays the same, but at least it will provide this solution, initial solution and next solution to the next interval, then initial solution, next solution, and so on. So we have more communication in times in some sense, but just to reorganize the system. And then let's see what happens when we do that. Well, that's just the first iteration and it works quite well. You see already, I solved exactly on the fine level, right? I solved exactly on the coarse level, and because the system is well built, then it works. Nice. So next idea, I know how to solve a diagonal using diagonal progression on this. So let's try to do diagonal SDC on the coarse sweep. Why not? And when you want to start this kind of thing, the first precondition you can use is actually backward Euler. It's really bad, but at least you know what it does. It has a lot of diffusion and it's parallel. So it's a good point to start. And what I see here, that for the first iteration, it's less accurate than what I have with the sequential backward Euler, but at least I do get something that works. And if I do the second iteration, yeah, it converges. Good. So now let's try to converge. So not looking at figures, but let's try to look at errors. So that would be the error over iterations. So that's my fast iteration. And that's the same iteration. The fast 2, I don't know how to name that. You can name 2 fast, fast 2, whatever.
More faster.
Yeah, more faster. I don't have any idea at this point. I'll let you actually decide on the name. But so we do have actually something that converges slower, but at least it's in parallel. So the coarse sweep can be done faster, which is nice. For instance, you can do maybe more coarse sweeps on the coarse level, and then it's like you do 2 course correction and then the relaxation. And at the end, because it can be done on parallel, and yeah, you get some time improvement, but I do lose something. Now, as I say, I started with this backward Euler in parallel coefficient. I can change. And what if I use this, for instance, this mean SRS coefficient? Then I try to rerun, I just have to change the coefficient. And actually what I get is actually an iteration that converges as fast here. So same convergence and can be done in parallel. So faster in some sense. And I didn't optimize the coefficients. The whole idea, I just use some coefficient that works for some other configuration. I plug it in and boom, it works. It doesn't mean that's the better one. I could probably find some coefficient that works better for this method here, but that would be another analysis. So that's what we have. And thanks to this whole understanding and analysis, designing new LLC method, I can also design new multi-level method like fast and other stuff that actually use that. And we have different level of parallelism. And I didn't start it on, I used the fine sweep, use some LU preconditioner, but I can use also diagonal preconditioner on the fine level. Why not? And then I have another degree of parallelism that I could use, but for later. So this can be applied to nonlinear problems. The only thing I have to check is actually the whole fast correction that has to be written down, but I guess it's more like writing pen and paper stuff. And you can optimize, as I said, the coefficients you want. So what you would have actually is more communication, but if you combine this with space parallelization, then at some point, when you increase the space parallelization, the communication you will have in time will become smaller and smaller. So it's not that bad. And because you're only considering small scale parallelism, you shouldn't pay that much on that. There is some, potential drawbacks. Just working on that quiz doesn't mean we'll work later on some PDEs, so you may lose something. There is some numerical stability that you have to consider. And of course, this method is nice when we write it with matrices and stuff, but as soon as you want to implement that in some large-scale problem, it becomes complicated. So at some point, we'll have to use research software engineering to actually code those methods properly so we can eventually try other combination and easily apply that to problems. So this is a really important aspect that we may have to care. Like we have to code everything in the correct way, because if not, then we lose so much time in trying to debug stuff that we won't know exactly how those method works on larger scale problems. And finally, I was a bit long, sorry for that. So a lot of analysis required, and that's actually something I intend to do when I have time. I want quickly to advertise for the SDC days. So we, since a few years now, we organize some mini workshop of 2 days of people who want to work on SDC. So the next one will be in December in Dresden. And if you are interested, contact the official organizer, which is his name. We'll be happy to have some interest for this workshop. So that's all. Thank you a lot for the attention, and thanks.
I think we might have time for one quick question for Thibaut while Lisa gets set up. So if anyone has a question. Well,
It's not a quick question, but a comment. So the intermediate algorithm you had, which solved the problem directly, would correspond at the algebraic multigrid level, the exact separation of red and black points will also get the valid solver. And what you do then is, instead of solving the coarse part exactly, you put the iterative method there. So this seems to be a direct application of an algebraic multigrid factorization. Did you think about this?
Yeah, I mean, I look at this, and at some point, the AC matrix, you can build that using some restriction of the. It's not exactly the same. It's interesting because you get different algorithm. I just
So this is this you cannot write like the algebraic multigrid.
not exactly algebraic. No, you because I still define the coarse matrix independently